Resistance is the property of an object that enables it to oppose the flow of electric current. Resistors are special components of circuits that are made for the express purpose of creating a precise quantity of resistance in an electric circuit. They are usually represented by a zigzag line or a small rectangular box. Resistors can be made from a variety of materials. When resistors are arranged in series, that is end to end, the effective or equivalent resistance is the sum of the individual resistances of the resistors. And when resistors are arranged in parallel, the inverse of the effective resistance is equal to the sum of the inverse of the resistance of each resistor. Connecting resistors in series, parallel, or a combination of the two helps us to get different resistances from a given set of resistors. You can differentiate a series connection from a parallel connection by seeing if you can move your finger along the wires from one point on the circuit, say point A, to another point on the circuit, say point B. If you can do this, then what you have is a series connection. If you ever encounter a point along the wire where you have to choose which wire to follow, then the circuit connection is not in series. If each circuit element provides an alternative path between the same points A and B, the circuit elements are said to be in parallel. Circuits can get really complex, and it pays to have a clear understanding of series and parallel connections to be able to handle such circuits. Given the connection on your screen, how would you find the effective resistance of the resistors if all the resistors have the same resistance R? We will do our tracings and calculations by looking at the most isolated, bite-sized chunks of the circuit, starting with the highlighted portion on your screen. Notice that you can trace the part of the circuit highlighted along a single straight wire without having to think of alternative paths. This means the resistors are in series, and the effective resistance for the resistors can be gotten by summing them up. We can then use the effective resistance to replace the three resistors in series. This is the resistor in another color on your screen. Next, we take the highlighted block. Notice that you cannot go through the resistors in a single straight path without thinking of choosing between alternative paths. Therefore, the circuit elements are in a parallel connection. We can now replace these two resistors with one resistor that is of equivalent resistance to the highlighted resistors. Looking at the highlighted part of the circuit, you will notice that the circuit elements are in a series connection. This means they can be replaced by an equivalent resistance equal to the sum of their individual resistances. This simplifies to what we have on the screen. The highlighted part is in a parallel connection, so we can get the equivalent resistance by using our formula for resistors in parallel. And finally, we have three circuit elements which are in series. So we get the equivalent resistance of the whole circuit by adding these three resistances together. And that is how you get the equivalent resistance between two given points in a circuit. Bye for now.